Well, hello, good people. Today we are talking about Newton's third law. Now, Newton's third law, you know it. It says for every action, there is an equal and opposite reaction. And I like to add the word force here and force here to help us know what we really mean by action and reaction. Or, as Mr. Hewitt says, forces always come in pairs. This is Newton's third law. Now, a lot of students have heard this nice little quippy phrase before, for every action there's an equal and opposite reaction, but that doesn't always mean that they really know deep down what that means. Now, when I start this class, I like to start by telling my students, okay, I want you to take, I'm going to make this bigger. I start by telling my students, okay, take your two hands and hold them up like this, and they do so. And I say, okay, now can you please give yourself a gentle high five? And the students do. They give themselves a gentle high five like this. I say, wow, that was very good. And I say, can you give yourself a very serious high five? And they say, yes, of course. And they clap their hands together very loudly. And I say, here's what I want you to do. I want you to take one hand, and with your left hand, can you please give a very gentle high five? Then with your right hand, can you please give a very serious high five? And they say, yes, okay. And the students really struggle with this. And they say, Miss Wilson, either both of my hands come away stinging or both of them come away feeling jolly. I can't give a very gentle high five with this hand and give a very serious high five with this hand. No matter what, they either both come away stinging or they both come away feeling fine. And I say to them, students, that is Newton's third law. For every action force, there is an equal and opposite reaction force. And that's what Newton's third law means. It means that you can't high five soft with one hand and really seriously with the other hand. Forces always come in pairs. Let's take a look at what we mean by this when we say that forces always come in pairs. Here's what we mean. What we mean when we say that forces always come in pairs is we mean first that you cannot give a high five without receiving a high five. If you high five your neighbor, they will high five you back. If you push on the table, you cannot push on the table without the table pushing on you. You know, because you can feel the table on your hands. Same thing, if I push on a wall, that wall is going to push back on me. I know that wall is pushing back on me because I can feel the wall on my hands. That is Newton's third law, is that forces always come in pairs. You will always, 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 if you put a force on something, that thing puts a force on you. Let's take a little look here. Wait. Sorry, I really want a highlighter because I'm super into highlighters now. It's kind of my thing. Okay, let's take a look here. There are two words in this sentence that I want us to pay attention to. We have, sorry, let's go down. Maybe like not that far down. Maybe like that far down. Okay, good. There are two words here that I want you to pay attention to. The first word is equal. That's like barely a highlighter. The first word is equal, and our second word here is opposite. Today in this video, we're going to start by talking about what we mean by equal, and then we'll talk about what we mean by opposite. Here's what we mean by equal. What we mean is you can't give a high five that's serious with one hand and a high five that's gentle with the other hand. They both have to exert an equal force on one another. If you high five hard with one hand, the other hand high fives just as hard back. Same thing, if I punch the table and I punch it hard, that table is going to punch me hard back. If I give the table a very soft tap, then the table taps me back very softly. But if I tap the table hard, then the table will tap me back hard, and I will feel the stinging on my knuckles. The size of the force that I apply is the size of the force that I receive. If I push on something hard, it'll push back on me hard. That is the rule. Let's check out a little example here. Suppose that, let's do this one. Okay, we'll do this one first. Once upon a time, there was a little bug. And this little bug was named Jerry. These are Jerry's wings, by the way, not Jerry's ears. Let's be very clear. Now, one day, Jerry was out flying around when Jerry encountered a giant car. Now, Jerry didn't just encounter this car in the way that one encounters a unicorn in the forest and you look upon it with wonder and amazement. No, that was not what happened. See, Jerry had a very close experience with this car. Because as Jerry was sitting there in the air, this car was coming zooming towards Jerry. And unfortunately, that was the last of Jerry as he ended up on the windshield of the car. A tough day if you're Jerry the Bug. Now, here's the question that I ask my students. I always ask, who experienced a bigger force, Jerry or the car? And students' first instinct will be to say, well, Jerry experienced a much bigger force. Look at Jerry now. But that's not what Newton's third law says. Newton's third law says that the force that the car put on Jerry is just as big as the force that Jerry puts on the car. The force that the car applies to Jerry is just as big as the force that Jerry applies to the car. But my students look at this and they say, no, Miss Wilson, that can't be the case. And here's the reason why they get confused, is because force is not the same thing as acceleration. We know from our video on Newton's second law that force is equal to mass times acceleration. Well, here's what we know. The force of the car on Jerry, well, Jerry has a very little mass. Meanwhile, the force of Jerry on the car, well, the car has a very big mass. So the car experiences the same force, but it has such a big mass that the car accelerates very little. Something little times something big gives you something medium. Meanwhile, Jerry has such a small mass that he accelerates a lot. And something small times something big gives you something medium. So both experience the same force. But when that force is applied to Jerry, Jerry goes flying. Well, in a new way, since he was flying before. And now, he's not. And yet, he is, flying at 70 miles an hour down the highway. Meanwhile, the mass of the car is very large. And so when it experiences this force, it doesn't accelerate it that much. It only accelerates it a little bit. Think about it in terms of inertia. Jerry has very, very little inertia. So when Jerry experiences a force, Jerry experiences a big acceleration. But this car really does have a lot of mass, and so it has a lot of inertia. So when it experiences a force, it does slow down. The car is slightly slower now because of its contact with Jerry. But its acceleration is much less. It accelerates very little. And so we can see that saying that for every action force there's an equal and opposite reaction force, equal forces does not mean equal accelerations. Try this one. Suppose that you were to go ice skating. And here is you, and you are ice skating. Wow, you look great. With your younger sister, Sarah. Now, suppose that you and Sarah both start on your ice skates, not moving here, in the center of the rink. And suppose that at the same time, you push on Sarah. Here is the force of you on Sarah. And suppose that Sarah pushes back on you. Wow, my arrow was way too long there. Sorry, team. Here is the force of Sarah on you. If Sarah is half as big as you are, will say that she has half the mass that you do. If Sarah's half as big as you are, who experiences a greater force? You or Sarah? Well, at this point, you say, Miss Wilson, oldest trick in the book, we experience the same force, but Sarah has half the mass that I do. So Sarah will have twice the acceleration that I do, because we'll both experience the same force, but she will experience twice as much acceleration for half as much mass because she has half as much inertia. First, we say for every action force there is an equal and opposite reaction force. Having an equal force does not mean an equal acceleration, but it does mean that the force between you is the same. Let's talk about what we mean by opposite. When we say opposite, we mean opposite in direction. Check it out. You push Sarah this way, and Sarah pushes you back this way. Jerry gets pushed on by the car this way, so Jerry experiences a force this way. Meanwhile, Jerry pushes on the car back this way. If I push on the table down, the table pushes on me up. If I am roller skating and I put my hands up against the wall, I push forward on the wall, and the wall pushes me backwards. When we say equal, we mean equal in size. When we say opposite, we mean opposite in direction. For every action force, there is an equal and opposite reaction force. Anyone who skateboards knows this, because when you skateboard, you know what you do. Here is my skateboard. When you skateboard, you take one foot off your skateboard, you put it on the ground, and you push backwards on the ground. When you push backwards on the ground, then the ground pushes you forwards. You push back on ground, ground pushes you forwards. And isn't that actually how we always walk? That is how we get around places. What we do is you take a step, and when you take a step, you put your foot down. That foot, wait, can you see? Okay, when you take a step, you put a foot down. That foot then has some friction, and that friction pushes back on the ground. And when you push back on the ground pushes you forward. Then you take your next step, push back on the ground pushes you forward. Take your next step, push back on the ground pushes you forward, and so on and so forth. Isn't that how we walk all the time? You know this if you've ever been canoeing, because you take your paddle and you put your paddle in the water. And if you want to go forward, well, then you swing that paddle backwards. You push backwards on the water, and the water pushes forwards on your paddle and pushes you forwards. Swimmers know this too. They know when they take a stroke, they push back on the water, and the water pushes forwards on them. This is Newton's third law. If you want to go forward, you got to push backwards. That's the idea. Now, here is a point of a tad bit of confusion for some students. Let's make this eraser big. Yes. Here's a point of a little tiny bit of confusion for some students. Here's what students say. Students say, okay, Miss Wilson, I hear what you're saying. We got forces that are equal in size and opposite in direction. And they say, okay, that all sounds good to me. But then they say, wait a second, Miss Wilson. You're saying equal in size and opposite in direction. Well, I just learned about how to calculate net force. And I learned that if you have two forces that are going in opposite directions, like one of them's going in the positive direction and one of them's going in the negative direction, then you subtract those two forces. And if you subtract those two forces and they're equal in size, well, then they would cancel out. When we talk about Newton's third law pairs, they do not cancel out. And let's talk about why that's true. Oh, no, stop. Don't do that. Go away. And you go away too. Okay. Suppose that I had a baseball bat, which I shall draw here. Yes. This is great. Okay. Yes. Doesn't that look like totally a baseball bat? You can just so tell that that's what it is. Okay, suppose that I have a baseball bat. And suppose that I have a baseball. Here's my baseball. And, well, okay, have a little bit of space for each other, okay? Okay, there's my baseball, and because we love colors, and colors are so important to us, we'll really make it look like a baseball. No jokes. Yes, now you can tell this is a baseball bat, and you can tell this is a baseball. That is pretty fantastic. Okay, suppose this. Suppose that you have a baseball bat and a baseball. The baseball comes in contact with the baseball bat, and the baseball bat pushes the baseball forwards like this. And we have the force from the bat on the ball. Well, when this ball comes in contact with the baseball bat, the ball will also push the baseball bat backwards. And this will be the force of the ball on the bat. Now, we know that these two forces are equal in size and opposite in direction. And the question is, why don't we subtract them out and why don't they cancel? And the reason why is in order to have net force. To calculate the net force, you have to calculate the net force that is acting on one object. Take a look. Suppose that I ask this baseball about its experience. This baseball doesn't know what forces are happening to the bat. It only knows its own experience. And if I said, baseball, tell me a little bit about your experience, ignoring the bat, the baseball would say, okay, well, yes, here's what happened to me. I was flying through the air, going this way. Then I got hit by a bat, and that force accelerated me so that instead of going this way, I changed directions, and I started speeding up this way. And so the baseball would say, I experienced a force, and that was one force. And so if I ask the baseball, but don't those forces cancel out? The baseball would say, what do you mean? I'm only experiencing one force. There's nothing to cancel out with anything because I'm the only one who's experiencing it and there's only one force to experience and one force can't cancel out with nothing. And I'd say, thank you very much, baseball, for that. That was very informative. Then if I go over to the bat and I say, baseball, bat, can you please tell me a little bit about your experience? The bat would say, why, yes, of course. I was swinging this way. And as I was swinging this way, then all of a sudden this ball came and hit me. And this ball slowed down my motion in the forward direction. So I used to be swinging this way fast, but now I started moving that way slower because I experienced one force that caused my deceleration. And if I said, wait, but bat, what about the forces? Why don't they cancel out? The baseball bat would say, what do you mean? I only experienced one force, and one force can't cancel out because there's nothing to cancel it out with. So here's the idea. If you want forces to cancel out, they have to cancel out acting on the same thing. If you have forces acting on two different objects, those forces can't cancel out because each object is only experiencing one of the forces. If, on the other hand, I had a baseball and the force of the bat was pushing it this way, here's the force of the bat on the ball. But then at the same time, I picked up my hand and I put it in the way so that that ball couldn't go anywhere. And so then the force of my hand on the ball, was this way. Well, then these two forces could cancel out because they are both acting on the baseball, and the baseball would say, I felt one push this way and another push this way, and those two pushes canceled out, and so I went nowhere. And that could work. These forces could cancel out because they're happening to the same object. These forces cannot cancel out because they are each being experienced by a different object. That is a little bit about opposite forces. They are equal in size. They are opposite in direction. They don't cancel out because they are acting on different objects. Now, there is one last thing that we will talk about today, and that will be our lesson for today, folks. And that is tug-of-war. You all remember tug-of-war from track and field day. Here is a rope, and here's how it would happen, is that you would have all the children line up on one side, and some children would be over here pulling the rope one way. Wait. Sorry, I can draw a child. And you can see this child is very happy because it's field day, and field day is so fun. And then you have another child over here, and this child is holding onto the rope here, like this. And this child is very happy. And the way that the game would be played is that they would blow the whistle, and the kids on this side would pull as hard as they could this way, and the kids on this side would pull as hard as they could this way. And whoever could pull the other team across the center line, well, that would be the winner. Well, suppose that in preparation for the big day, for the big field day, Charlie, this is Charlie, obviously, and Carly, that's Carly, were practicing. And so they went out into their backyard and they got a giant rope and they started pulling on it and playing tug-of-war. Here's a question. Suppose that Charlie pulled on the rope with a force of 100 newtons towards himself. And suppose that Carly also pulled on the rope with a force of 100 newtons towards herself. Here are two questions for you. The first question is, what is the net force acting on the rope? And the second question is, what is the force of tension in the rope? Now, most students say, okay, Miss Wilson, the net force acting on the rope, well, that would be 0 because you have one force pulling this way, one force pulling this way. Those two forces will cancel out, and so the net force on the rope would be 0. And they say that really does make sense because this rope appears to be in a state of equilibrium. It's not going to accelerate towards Carly. It's not going to accelerate towards Charlie. It's just going to stay right where it is. And so they say this is a state of equilibrium. The net force is equal to 0. We got none acceleration. And I would say, yep, absolutely true. Then the next question is, what is the force of tension in the rope? And most students will say the force of tension in the rope is 200 newtons. And that is not correct. The best way to think about tension in the rope, because tension in the rope is kind of a hard thing to picture. But you can think about, and well, sorry, let me give my whole caveat and then I'll come back. The reason why it's hard to talk about tension in a rope is because most of the time we talk about how a force is applied to something. So we can talk about the force on Charlie or the force on Carly. But it's difficult to talk about the force of tension that is inside the rope. That's a weird way of talking. And so I tell students that the easiest way to think about the force of tension is to think about the forces of tension as the force that the rope is putting on something else. That's the easiest way to think about it. The force of tension in a rope is the force that the rope is putting on something else. Let's go ahead and see right here. Right? Actually, let me change my color. Yay, color changes are so fun. Okay, at this point in the rope right here, Charlie is pulling the rope this way with a force of 100 newtons. Which means this part of the rope right here has to pull back on Charlie with a force of 100 newtons. That is Newton's third law. Charlie pulls with 100 newtons and the rope pulls with 100 newtons. Now at this point, I say, so what's the tension in the rope? And some students will say, 0, Miss Wilson. And I will say, no, it's not 0. Imagine this rope. Imagine a rope with a force of 0 tension. A rope with a force of 0 tension goes blah, blah, blah. It's just a kind of floppy rope. Does this rope seem to be floppy right now as Charlie and Carly both pull on the rope? Pfft, no! This rope has some tension in it. And the tension in the rope is how hard the rope is pulling on something else. It's how hard the rope is pulling on Charlie. So the tension in the rope at that point right there is 100 newtons. Then I say, okay, students, check it at this point. What's the tension in the rope right here? And most students will say, okay, well, Carly is pulling on the rope with a force of 100 newtons. That means that the rope has to pull on Carly with a force of 100 newtons. And I say, very good, so what's the tension in the rope at that spot? And they say the force of tension in the rope at that spot is 100 newtons because it has to pull back on Carly with an equal but opposite force. And I say, very good. And I say, okay, take a look right here. What's the force of tension right here? And I say, tricky. Here's what I say. Okay, well, this spot, really, basically, it is being pulled on by this piece of rope here and by Charlie. This piece of rope is being pulled on by Charlie plus this little section of rope with a force of 100 newtons. So this little part of the rope would have to pull back on Charlie and this section of the rope with a force of 100 newtons. So the tension right here would be 100 newtons. And I say if I went right here, the force of tension in the rope right here, well, right here, it's getting pulled on by Charlie with a force of 100 newtons. So this little part of the rope would have to pull back on Charlie and on this section of the rope, and it would have to pull with a force of 100 newtons because it's getting pulled on with 100 newtons. And I say same thing over here. This little part of the rope right here would be getting pulled on with a force of 100 newtons by Carly, and by the next little section of the rope is also helping to pull it with a force of 100 newtons, so it would have to pull back with a force of 100 newtons. So the tension in the rope right there would be 100 newtons. And right here, the tension in the rope would also be 100 newtons because it has to pull against Carly, which is pulling with 100 newtons. And I say so on and so forth. Here it would be 100, here it would be 100, here it would be 100. And what's the tension all throughout the rope? And all the good people say 100 newtons, Miss Wilson. And that is correct. If this whole tension thing is a little bit confusing to you, you can think about the rope kind of just like a force extender. Imagine if the rope were not truly a rope, but imagine if Charlie's arm just got really, really, really long and held onto Carly's hand. If I asked you, how hard is Carly pulling on Charlie? You would say 100 newtons. If I said, how hard is Charlie pulling up Carly? You would say a force of 100 newtons. And if I said, what's the tension in his arm? You would say 100 newtons. If his arm wasn't like that, let's say that his arm, let's say that his arm wasn't like that. Let's say that his arm only went to here. If his arm only went to here, he would pull on this section of the rope with a force of 100 newtons. Carly would pull back on this section of the rope with a force of 100 newtons. This section of the rope would pull on him with a force of 100 newtons. This section of the rope would pull with a force of 100 newtons, and the tension in the rope would still be 100 newtons. You can kind of think about the rope as just a force extender. It extends Charlie's force all the way over to Carly. Here's another way to think about this. Suppose that Charlie said, I've had enough practice for today, and Charlie went in for lunch, and Carly said, I'm still here to practice, so she replaced Charlie with a pole. And suppose that she tied a rope around the pole, and Charlie was no longer there, and instead of Charlie, it was a pole. If Charlie was no longer there, and instead of Charlie, it was a pole, and I asked you, how hard is Carly pulling on the rope? And she's pulling with a force of 100 newtons. And I said, how hard is the rope pulling back on Carly? You would say with a force of 100 newtons. And if I said, how hard is Carly pulling on the pole? You would say, Carly's pulling on the pole with a force of 100 newtons. And the pole is pulling back on Carly with a force of 100 newtons. So all throughout the rope, the tension is still 100 newtons. This is how it's easiest to find the tension in the rope, is we talk about how hard is that rope pulling on something else. That's the easiest way to think about it. Now, here's where we get to a little bit of what I call the Newton's third law tug-of-war struggle. Here's the Newton's third law tug-of-war struggle. Suppose that Charlie came back from his snack break and he said, okay, actually, Carly, I've realized we need to keep practicing, and in fact, we need to up our game. And he said, I'm going to start pulling now with a force of 150 newtons. If Charlie pulls with a force of 150 newtons on the rope, well, then the rope's going to pull right back on him with a force of 150 newtons. If he now put a tension in the rope of 150 newtons, that means now if he's pulling on the rope with 150 newtons, he's also pulling on Carly with 150 newtons. And so the rope would pull on Carly with a force of 150 newtons. Well, then, if the rope is pulling on Carly with a force of 150 newtons, then Carly would pull back on the rope with a force of 150 newtons. Well, let's say that Carly says, actually, I think that I'm going to up my game. And let's say that Carly pulls on the rope with a force of 200 newtons. If Carly pulls on the rope with a force of 200 newtons, well, then the rope is going to pull back on Carly with a force of 200 newtons. And then that tension is then going to transfer so that Carly is, via the rope, pulling on Charlie with a force of 200 newtons. And then if the rope is pulling on Charlie with a force of 200 newtons, then he's going to pull with a force of 200 newtons. And then if Charlie says, actually, I'm upping my game and now I'm pulling with a force of 250, do you see then how the rope is going to pull with a force of 250 and then it's going to pull on Carly with a force of 250 and then Carly's going to pull back with a force of 250. Here's the thing. Here's the problem. The Newton's third law, tug-of-war struggle, is that if you pull harder on the rope will just pull harder back on you. And then if you pull harder on the rope and the rope pulls harder on you, then the other team will just pull harder on the rope. And so here's the secret of tug-of-war. The way to win tug-of-war is not by pulling on the rope harder. If you pull on the rope harder, that will just make the other team also pull on the rope harder, and the net force will still be 0, and no one will win. The way to win a game of tug-of-war is with your feet. If you're trying to win a game of tug-of-war, what you should do is you should push on, wait, let me draw it better. You should push on the ground. Oh, no. You should push on the ground. That is cutting off. Okay, it's all fine. Okay, you should push on the ground. Because if Carly pushes on the ground this way, then the ground will push on Carly this way. And if Carly's holding onto the rope, then Carly will move this way and she'll carry the whole rope with her. If Charlie wants to win, then Charlie should push on the ground this way, because then the ground will push on Charlie going back this way. And if the ground pushes on Charlie this way, and Charlie happens to be carrying the whole rope with him, then he will pull the rope back with him. This is how you win a game of tug-of-war. You don't pull on the rope harder than the other team, you push on the ground harder than the other team. That will create a net force on the rope that will cause the rope to accelerate in the direction that you want it to go. One last example for you for today. Suppose that you had a horse. Here is a horse. Wow. Okay, that's not a very good horse. Here's a horse. That is much better. And wait for it. Wait for it. Ah, yes, a very good horse. This is a horse. This horse's name is Kenny. Now, suppose that you have a horse, and you have told your horse, you need to carry this cart of goods here, because we are going to take our goods into town. And Kenny says, actually, I don't think so. And you say, what do you mean, Kenny? What's wrong? Why can't you carry the cart into town? And Kenny says, well, you see, I would carry the cart into town, but I just learned about Newton's third law, and it seems that I can't. You would say, Kenny, what do you mean? Why can't you carry the cart full of vegetables into town? And Kenny would say, well, because here's the problem. I would love to carry this cart, except that if I pull on the cart will just pull back on me. And so, unfortunately, if I pull on the cart pulls back on me. Well, we are at an impasse, and it appears that no one can go anywhere since those forces will cancel out. What would you tell Kenny? Well, you should say, Kenny, no worries. You can still make it to the market today. What you should do is you should push on the ground. If Kenny pushes on the ground, then Kenny pushes this way on the ground pushes forwards on Kenny, and then Kenny, who's attached to the cart, can go with the cart forward in the positive direction towards town. And that is just about all that we have for today, folks. Today we talked about Newton's third law. We defined what it was. We talked about how forces are equal in size, which does not mean equal in acceleration. It means equal in force, but objects with different masses will experience different accelerations. Then we talked also about how those forces are opposite in direction. So if you want to go forward, you have to push something backwards. That thing that goes backwards will push you forwards. Then we also talked about how in a game of we talked about why those forces don't cancel out. Then we talked about how in a game of tug of war, the way to win is actually not to pull on the rope harder, it's to push harder on the ground. And that's the same situation for Kenny here with his little tug of war problem, but it's not tug of war, it's a cart. Kenny can push backwards on the earth, and that will allow the earth to push forwards on Kenny. And that, ladies and gents, is just about all we have for today. I hope you have a wonderful, wonderful rest of your day. Bye, good people.